Hey everyone, welcome back to this video review series on differential equations and some of the mathematic background required to really get an understanding of system dynamics and control. This video is going to be kind of more of a motivating example video that'll take us through, where do these differential equations that we're dealing with come from? What are some methods that we can use to solve them? And why might relying just on pure, calculus alone be more of a challenging thing than we would maybe care to admit? And like, why do we need these tools that we learned in our differential equations class? So we're going to start with the first example you'll get in most textbooks, the same example I got when I took system dynamics. It'll be the first example you probably read in the differential equations textbook. In fact, it is the same one that I had in my book by Boyce and even in the Palm textbook. And it's the classic example of a ball in free fall. So let's just say that we have a ball in free fall. We're not going to assume any air drag, and its equation is going to look something like this, where sum of forces in the x direction, which we've defined positive as down, is going to be equal to mx double dot, where m is the mass of the ball. And in this case, the sum of our forces is just going to be equal to gravity. We're going to have an mg right here. So that's the force due to gravity. We'll draw that in right over here. And in this case, if we're neglecting air drag, this is all we've got, right? So first things first, you might already notice that in this equation that we have right here, our m's will cancel out, and we're left with the pretty basic equation, x double dot is equal to g. So great. We want to know something more about this equation, right? If we wanted to know, for instance, what the velocity is, how do we get there? And the easy answer for this is that we're just going to go ahead and integrate. Now, this being said, I want to pause to reflect on the fact that this is already a differential equation, maybe the most basic differential equation you're ever going to get. And it's a differential because our equation has a derivative in it, x double dot. It's the second derivative of position. So we'll integrate it one time to get velocity. So doing our one integration, and so the integration is going to look like this. We'll have the integral of x double dot is equal to the integral of g. And the integral of our acceleration is going to be velocity. So we're going to have now x dot is equal to gt plus our constant of integration. And I'll give it capital C for that. Great. We now know something about how the velocity of this ball is going to behave over time, but what if we wanted to do position? Well, again, we can integrate this. We'll have the integral of x dot is equal to the integral of gt plus capital C. We can distribute that integral in, and then we're going to get the integral of x dot is equal to the integral of gt plus the integral of capital C, and these integrals are with respect to time. I know I'm being a little loose with notation there, but that's going to give us x is equal to 1/2 gt squared, and that'll have some constant of integration associated with it. Maybe I'll just call that f for the moment. Then we'll have plus the integral of c, which is going to give us ct plus some constant of integration with that. Maybe we'll call it g. Now the beauty is that some constant plus some other constant is just a constant. So what we can do is simplify this to 1/2 gt squared plus ct. I'm just going to call that new lumped constant d. So we kind of were able to integrate out that differential equation to kind of get our to exactly get the three equations that we'd primarily be interested in. But something to note is that probably a lot of people are already recognizing what this differential equation looks like, the position solution looks like. And you'll recognize that as the kinematic equation. The thing that's really important to note here is the assumption that was made to get this equation. This is not an equation that you're going to be able to use for almost really any other problem you're going to solve in your differential equations career, which was that this assumed that you had a constant acceleration. Right, gravity was our constant acceleration, so we were able to integrate to get this because g was constant. This does not work for problems where your acceleration is not constant. Really important to know right from the get-go. If you're watching this video in preparation for a quiz and exam and you have a non-constant acceleration in your differential equation or your system dynamics class and you write that down, it's probably not going to end well for you. All right, so I just harped on the fact that, you're never really going to have problems where it's a constant input, constant acceleration. So let's add a little something to this problem to make it more realistic to what you're going to see in a system dynamics class. So we're going to have our same ball with mass m. We're going to have our position x going downwards. So we're still going to have mg. We're going to have our gravity force pulling us down. However, this time we're going to add in a linear air drag effect. And our linear air drag is just going to be some damping constant times our velocity. So BV, and it will be opposing motion. Our damping is going to oppose our motion. Another way that you could write BV is BX dot, right? Those are the same. So now when we come to do our sum of forces, we still have our sum of forces in the x direction. It's positive downwards. Sometimes I know that's kind of sloppily written. I like to put my notation for what frame is positive in what direction next to my sum of forces so I don't get confused. That's going to be equal to mx double dot. And now we have mg pulling downwards, and then that's the positive direction, and then minus bx dot, because this is a opposing motion. It's in the negative x direction. So now let's say we want to solve this. So this could be difficult depending on what you want to do. Something you can notice though is this looks like a second order differential equation, and our order here is being defined by what's kind of the highest order derivative in our equation. In this case, it's x double dot, so we would say this is a second order differential equation. However, right, we don't have any terms that are just a base x term, right? So the fundamental differential equation that we're trying to solve is actually first order. It's a little bit maybe tricky to notice the first time, but we could rewrite this equation without changing anything besides kind of how we're writing this to be mv dot, because the derivative of velocity is acceleration, so v dot is the same as x double dot, is equal to mg minus bv. So this is the exact same equation, but now it's a first order differential equation we're trying to solve. And again, it's really important that you're able to recognize how those two equations are the same. If you're confused, I would say just pause now and try to work this out in your head. But all it is just saying that x double dot is equal to v dot in the same way that the change in your position with respect to time is velocity. So it's just kind of taking advantage of those two relationships. Okay, so now say we wanted to know what the position of our ball is going to do with respect to time, and we need to integrate this equation right here. Okay, right, seems simple enough. We just need to integrate this out. So we'd have our integral of mv dot is equal to distributing through the integrand mg minus integral bv. But in this notation, there might be something that's a little bit lost because while we can for sure integrate this term here, we can integrate mg, both terms are constant, this term, the integral of bv, is now very much less straightforward to integrate because v is not a constant anymore. V could probably more accurately be written as v of t, right? Velocity is a function of time. Velocity is going to be a function of the acceleration that we're experiencing. And if we look back at the very top differential equation, our acceleration is a function of velocity, and now our velocity is a function of acceleration. So there's not like a clear derivative of v. You can't just integrate that one term. Now, we can still apply some calculus to solve this, and we're going to work through that now. But the motivation for working through solving this differential equation using pure calculus is to motivate how much it kind of stinks, right? There's got to be a better way, and future videos will focus on that better way. But we can apply calculus to solve this problem, so let's go ahead and do that. I'm going to go ahead and erase this right now, and we're going to just apply basic calculus and have to use a u substitution to solve this. So we're going to rewrite the whole equation. We're going to write mv dot over mg minus bv is equal to 1. And we want to integrate this equation. So we're going to integrate this from t0 to t. We'll integrate this from t0 to t as well. And to do this, we're going to use our u substitution. So we're going to say that u is equal, is equal to mg minus bv, and taking the derivative of u with respect to time, so du dt, well, mg is not a function of time at all, so that's going to be 0. And then v is going to be minus b v dot. Again, it's not just minus b because v is a function of time. The derivative of v is not just, 1. It's not just a constant. If we took the derivative of v with respect to v, that's one thing, but this is a derivative of v with respect to time, so it comes out a little bit differently. So we now have du dt equals minus bv, and now we can say that du is equal to minus b v dot dt. All right, so rewriting our equation to make very explicit what we're doing, we're going to focus on the left-hand side of this differential equation. We have our integral from t0 to t of mv dot over u, and there is a dt right here. But we can solve for dt from the previous equation and get that dt is equal to du over minus b v dot. So plugging in for dt there, this equation becomes integral of t0 to t is mv dot over u, and then we're subbing in for dt. We are going to have now here a du over minus b v dot, so these v dots go away. We can pull the minus b over m out of the integral, and then rewriting everything all together, we're going to have a minus m over b integral from t0 to t of 1 over u du equals the integral from t0 to t of 1. So this is the full integral, and not to lose track again of what we're trying to solve for here at the end, we are trying to get to what is the velocity of the system doing in time, and this is how we're going to do it. So the integral of 1 over u du is pretty straightforward, so we're going to go ahead and solve out both sides of this integration. We're going to have minus m over b. That's going to be multiplied by ln of u evaluated at t equal to time 0 and time equals t. And then the right-hand side of this is just going to be t minus t0. So I'm going to go ahead and multiply across by minus b over m, and then we'll evaluate that integral on the left-hand side. So we're going to get ln, and plugging back in for u, where u was mg minus bv, we're going to have mg minus bv of t, and then we're going to have minus ln mg minus bv naught is equal to t minus t0 multiplied by minus b over m. Great. All right, so what we're trying to solve for now is now readily apparent. V of t is right here. We just need to do all the algebra required in order to solve for v of t. One thing we can do is apply an exponent law. So and we have e to the a minus b is equal to e to the a over e to the b. And what's great is here a would be our natural log term, and b is also our second natural log term, and e raised to that like natural log is just going to be 1, and our remainders will only be what's inside. So we can essentially rewrite the whole left-hand side as a fraction. But if we're going to raise the left-hand side to an exponent, we got to do that to the right-hand side too. So let's go ahead and do that. It's a big step, but you can work through and plug in everything if you want. We end up with mg minus bv of t over mg minus bv naught is now equal to e to the minus t of 0 times b over m. All right, things are starting to take shape. Again, we're trying to solve for v of t. We can multiply over by the denominator of the left-hand side. We get mg minus bv of t is equal to e to the minus t of 0 times b over m. And now this whole thing is being multiplied by mg minus bv a time equals 0. And then we can just rearrange this now to solve for v of t. I'll do it in 2 steps where we just kind of move a few things over. We'll have minus bv of t equals e to the minus t naught b over m, mg minus bv naught, and that's going to be minus mg. All right, so now we'll divide through by minus b on both sides to isolate v of t. So we'll have v of t is now equal to e to the minus t is t sub 0 b over m. And now this is going to be v naught minus mg over b plus mg over b. All right, so it wasn't pretty, it wasn't easy, but we were able to get the solution of what is the velocity of this ball doing in time with pure good old calculus. But there's a few things that it would probably be a good idea to point out. The first thing that I want to point out is kind of the structure of exactly how this differential equation is written out. So at time equals 0, so if we say that t of 0 is equal to 0, and that means also just t is equal to 0, time equals 0, then this exponent term here is equal to 1 because you have e to the 0, and 0 is 1. So you'd end up with v of t is equal to v naught minus mg over b plus mg over b, right? We're just left with velocity at time equal to 0, which, so really that should be v of 0 equals v of 0, right? These are some of the sanity checks that you can do to make sure that the solution to the differential equation you're getting is right. You know, plug in a couple of edge cases and see what happens. The other thing is, okay, well, that's what happens at time equals 0. There's no point really in looking at negative time because we don't, I mean, what does that exactly mean? Like, you know, what happens though as time goes to infinity, right? As time trends up towards infinity, you end up with e to the minus infinity, and that is going to trend to 0. So over time, anything that's being multiplied by that negative exponential, and again, that is a negative infinity, right? If it's a positive exponent, then it's going to grow to infinity, but negative, like e to a negative, massive number goes to 0. Everything multiplied by that exponential is going to decay to 0. So as time goes to infinity, v of t is going to go to mg over b, right? So this is going to be what we call our steady state behavior. It's steady state because the steady state part of our equation is not affected by time. Conversely, anything that's multiplied by the exponential is going to be called a transient term. The transients disappear in time. So let's go ahead and, I guess, write this out now. Again, we have v of t equals e to the minus t of 0 times b over m, and that's being multiplied by v at time 0 minus mg over b plus mg over b. So we look at this, and now everything here is being multiplied by that decaying exponential. So this is the transient. These are transients. We're going to have an entire section in this class dedicated to transient response. And this right here is the steady state response. So basically, once all the dynamics have decayed out in time, what's the system doing once it's reached? This would essentially be your steady state is your terminal velocity. And I think there's other things that the beauty and the intuition of differential equations really comes out to shine, where, okay, we want to know what happens if our damping term, right? B is the damping term. I should probably just put a star instead of an arrow there. If the damping term increases, then that fraction is going to get smaller, which means our terminal velocity is going to be lower. That makes sense. That's kind of the whole premise of parachutes, right? And if we make it a lot smaller, our velocity is going to grow. So there's a real beauty and intuition to these differential equations. There's another way, though, that we could write this entire differential equation. It's exactly the same. We're going to rearrange a few of the terms now. So this is the new way that we can write our differential equation. And instead of saying transient and steady state, we're now going to have a free response and we're going to have a forced response. So the free response is purely dependent on the initial conditions of the system. So dependent on our initial conditions. The forced response is not dependent on the initial condition. It's only dependent on the forcing function. In this case, the forcing function is just gravity. The input, the force caused by gravity, our mg over b, is what's driving that response. So this is dependent on the forcing function. And so what we'll see in this next video that we're going to look at is this structure of a free response and a forced response is paramount to how we're going to solve these differential equations. We're going to look at a homogeneous differential equation, which we'll talk about more. That means we're going to look at the response when there is no input to the system, and that will allow us to solve for the free response of the system. And then we're going to look specifically at what's the response to the system with an input, and then that will give us our forced response, and also called the particular solution to the differential equation. So our free response will give us a homogeneous solution. What does it look like with no input? And then we'll derive the forced response from the particular solution to a differential equation, and we can add those two together. When you solve for the homogeneous and particular solutions and you add them together, that gives you the solution to a differential equation. So I hope this has been at least a good motivation into why we need differential equations, why we don't want to rely purely on calculus. The next video will dive more into exactly how we're using these tools in differential equations to get the solutions to these differential equations in a much easier way. Again, this video is purely to motivate how quickly the difficulty can ramp up in trying to solve these equations. In fact, air drag is typically nonlinear. It's normally a BV squared term, and we didn't even look at that, right? We're even already using simplified air drag in the equation that we had. And it already was, a little bit of a pain. And then imagine once you start getting into coupled differential equations, the complexity just ramps up exponentially, some pun intended. And so, yeah, I look forward to explaining a little bit more in the next video. Thank you guys. Bye.